Okay, so in this problem, we've got refrigerant 134A, 16 bar, 100 degrees Celsius. I'm going to determine the specific volume two ways. First way is using the table, which is probably the preferred method, and then the second way is using that compressibility chart. So let's start by using the table, easiest and most exact. So this would be the way to do it, but I'm going to show you that you get the same answer either way. Okay, so I go into table A2, A12. Okay, and I'm at 16 bar and 100 degrees. So the 16 bar table is down here, and 100 degrees is this guy right here. And you can see my volume is 0.01601. Okay, so for that one, it's very easy. It's 0.01601 cubic meters per kilogram. Again, that is the preferred way to do it. It's the most exact and generally the quickest and easiest way. Now, the other way we're going to do it is using the compressibility chart, which is this chart right here. Okay. Notice what I need for this. I need a reduced pressure and a reduced temperature, which is the temperature and pressure that I'm at compared to the critical temperature and pressure of what I'm dealing with, which is R134A. Okay. So I go to table A1, where it has all of the things. I've got molecular weight, and then I've got critical temperature, critical pressure. So I'm going to jot all three of these down for 134A. So the molecular weight is 102, critical temperature is 374, and critical pressure is 40.7. So let me jot that down. Now that temperature was in Kelvin, so just be aware of that. So M for this, again, is 102.03. TC, critical temperature, is 374 Kelvin, and PC is 40.7 bar. Okay. Now, I need to find the reduced pressure and the reduced temperature to look it up in that table, that chart that I've got there. Okay. So PR then is my pressure, which is 16 bar, divided by 40.7 bar, which is going to be 0.393. And my reduced temperature, again, is 100, which is 373 Kelvin, divided by 374. We're going to call that 1. Okay? So I'm going to use this reduced pressure and this reduced temperature to calculate what we're going to call Z, which is the compressibility factor. Okay? So again, I've got reduced temperatures going this way, right? So this line right here is a reduced temperature of 1, which is where I'm located. Again, temperature divided by the critical temperature. And then my reduced pressure is just shy of 4. It's 3 or 0.39, so just shy of 0.4. So I'm going to follow this temperature line back until I hit just below 4, which is right about here. Which as I slide over is pretty much 0.86, right? So again, you bring this up to T equals 1, which is right about here, slide over, and I'm about Z of 0.86. Now, as you can see here, Z is PV over RT. Okay, I'm going to use that relationship to figure out what my V is, right? So Z is PV over RT. Right? So solving this for V, I have ZRT over P, okay, where Z is 0.86. R, okay, is my constant, which is right there. and I'm going to do it rather than kilojoules per kilomole, I'm going to use joules per kilomole. Okay, so I'm going to use 8314. Okay, but notice this is R bar. Okay, this is R, so I need to take that R bar and divide it by the molecular weight of 102.03 so that I can get the actual R rather than R bar. This is R bar. To convert it to R, I just take that constant and divide it by the molecular weight of what the substance is that I'm using. Okay. Then I take that times my temperature, which is 373 Kelvin. And then I divide that by my pressure, which is 16 times 10 to the 5th. So calculating that for V, I get 0.01634. Now that's very close to the value up here. However, it's not as exact because that chart is pretty hard to manipulate, okay? And it took me a lot longer. So if you have a table, use the table. Okay, this is only good for non-ideal gases, okay, that I don't have a table for.